Good morning, everyone. I'm Liza Lester from AGU. I'm happy to welcome you here to our 9 o'clock press conference, Heart of Io's Rage. We have folks here from our JPL team with us, Delia Santiago Martirez, Scott Bolton, Ryan Park, Alessandra Mura, and Heidi Becker. That's from left to right. They're going to speak from you from here, from the table, for about 20 minutes, and then we'll open the floor to Q&A. And with that, I'm going to turn it over to our panel. Thank you.
Thank you, Liza. I'm excited to be here on behalf of NASA headquarters. When most people think of Juno, they likely think of images like this of Jupiter, taken by Juno Cam. However, today we are here to discuss one of the other exciting targets of Juno. And since Juno arrived in inserted in Jupiter's orbit in July 2016, it's been making incredible discoveries about the planet of Jupiter and its atmosphere, structure, and the magnetosphere. In 2021, it completed its extended mission and it completed its primary mission and began its extended mission when it expanded its discoveries. One of the exciting targets of the Juno extended mission has been the Jovian moon of Io, which is the innermost of the 4 Galilean satellites. Today, we're fortunate to have members of the Juno science team here to discuss a paper on the source of Io's volcanism that has been published today in the journal Nature. I'll turn things over to Juno principal investigator, Dr. Scott Bolton of the Southwest Research Institute. Scott, over to you.
All right, thank you, Delia. That was great. So we're here, today is really great to be here to sort of share the results that we have. Io is one of the most intriguing objects in the whole solar system. It's about the size of Earth's moon, so it's a relatively small moon, but this little moon is the most volcanically active body that we've ever seen in our solar system. And Juno was fortunate over the years to actually see for the first time both poles. It's gotten observations of the North Pole and the South Pole now, and we can see that this body is completely covered with volcanoes over both poles, all across its middle, constantly going off. So how does this really happen? Why is Io, so different than everywhere else that we've seen? Where are all these volcanoes coming from and what's driving them? And the answer is Io is orbiting a monster, Jupiter. And so Jupiter is so massive, you could put all the other planets in our solar system and they would fit inside Jupiter and still be less mass than Jupiter. So the short story is that, Io is actually orbiting this monster. And as it goes around, that orbit is not perfect. And so it's a little closer sometimes, a little further. And basically, Jupiter is squeezing the insides out of Io. As it goes around, it's constantly getting squeezed. And just like if you take one of these rubber exercise balls and you squeeze it a whole bunch of times, it starts to get warm. That's what's happening inside Io. That squeezing is generating heat. And it's getting so hot that its insides are literally melting and popping out. The eruptions are nonstop, constant. It's like a nonstop rainstorm. It's just always erupting all over the place. And so what's really happening? How's that squeezing going on? And so scientists call tidal forces. And this is very similar to what our moon does here to us on Earth as it goes around. It raises the tides of our oceans or our seas, and you can see that, on a monthly basis. You'll see these tides go up and down as that orbit goes around. And that's basically what's happening to Io. It's going around and it's feeling the tidal forces from Jupiter. Now, Jupiter does this to all the moons in its system. It's so huge. Io's closer, so it feels a stronger effect. But basically, Jupiter's tidal forces and just its squeezing is what creates the oceans, the water oceans that are inside of Europa and Ganymede that were, headed out with 2 other spacecraft that we'll be able to explore sometime in the future. So this tidal force can create oceans. And so one of the big questions is so Is Jupiter's squeezing of Io creating an ocean inside of Io that's not made of water, but made of lava? And so that's one of the big questions that's been out there since since the volcanoes were first discovered at the time of Voyager. And it's still an outstanding question. Even just last year, some scientists took and saw the data that we had, that Juno had collected over the poles, and realized that the whole place was covered with volcanoes. And they used that data to hypothesize that it was evidence that there was a global magma ocean underneath. And that was what was driving it. So this question is not only historically old for decades, but it's still currently being debated. And so we have results today that you're going to see where we really do know the answer of that now. And so you're going to hear from 3 different colleagues that are on Juno, co-investigators. Ryan is going to actually show you some data and discuss the results of whether there really is a global ocean magma inside of Io. Alessandro is going to talk about results from the Juno infrared camera, which is providing new insights on the characteristics and how the lava lakes, the lakes made of lava, work on Io. And then Heidi will show Juno visible light images that are seeing the first evidence that tectonic activity is also playing a role in the volcanoes. It's not just that they're coming up and erupting, but the same tectonic activity that may create and disrupt mountain ranges may be associated with volcanoes as well. So it's not just the volcanoes building the mountains, but the mountains may be building the volcanoes too. Now, before we pass it on, I have a little animation that I'll show you that sort of illustrates all of these little topics that I'm showing you. It's made basically from real images of Io, and where the goal is to take you there, and so you can see what it's like if you were to be able to visit Io, and someday maybe we will. Now, while it's based on real images and based on scientific analysis, we do take an artistic license and actually show you close up things that are from a different perspective than we were able to get on the spacecraft. So what's on this little movie that you're going to see is a mixture of real images and artistic renderings of what we think are there based on our scientific data. Now, because there's an artistic license in there, I just want to make it clear that someday when you go land on the edge of a lava lake on vacation, it may not look exactly the same. And that would be very useful if you take a picture of that and send it back to us. We'll update our models. Okay, so let me click ahead. So here's a picture of Io, and you can see that this is basically, when I first saw this, when Voyager was going by, to me it looked like a pepperoni pizza, and that's because of all the volcanoes that were going on. And so here's the animation. And so you'll see a plume as we approach Io. And there have been, although Juno did not see this exact plume, there were other spacecraft like New Horizons and Voyager that actually captured a lot of these plumes. We've seen some, not quite, and we've made this animated so you can actually see it in motion, how we think it works. Here's what the lava lake may look like. This is, of course, a crusted lava, and then some hot still with lava fountains coming up. And Alessandro will talk more about this. And then as we go around and turn around from Jupiter, you'll see the more global image, again, with 2 plumes. And there are many that are going off at once. We know this because they're all active at the same time, almost like a constant storm. And when you peel it open, this is one of the basic questions, is what does it look like inside? This is what we think it might look like, and Ryan will explain what those different components are. So with that, I'll pass it on to Ryan.
Okay, thank you, Scott, and good morning, everyone. So I'll be diving a little deeper into what Scott just talked about. Specifically, I will be covering what we have learned about the interior structure of Io, okay, based on the gravity data collected by Juno 3 Io flybys. So This slide shows some of the images of Io taken by Voyager 1, Galileo, Juno over 44 years. Okay. One of the common things that you'll see is that Io is volcanically active. In fact, as Scott mentioned earlier, Io is the most volcanically active object in our solar system. Then you might start wondering, okay, what is the driving energy source for all these volcanoes and what is fueling them? Scientists believe that this energy comes from tidal forcing, or tidally driven, which is very similar to how the tidal ebbs and flows on Earth works. So since Io is in elliptical orbit around Jupiter, its distance from Jupiter changes, so that gravitational pull from Jupiter changes, causing Io to go through tidal flexing, which introduces enormous energy. And scientists theorize that it may be hot enough, or the heat might be significant enough to melt Io's rocky interior, so that it may form a global subsurface magma ocean. So mystery, or the question that has been out there for over 40 years, well, does Io have a global magma ocean or not? And we are here to share our data and present our results showing or presenting what Io's interior looks like, although you might already know what it may look like. So let me start with some basics. Okay. So Io is an elliptical orbit around Jupiter. Okay. So if you look at of course this is not drawn to scale, okay, but if you look at where Jupiter is, it's not exactly at the center. Okay. Which means Io has the closest point and farthest point. So at the closest point, Io's tidal bulge will be at largest. Okay. I mean, just like ebbs and flow, you have a tidal bulges. And as Io travels on its orbit and goes to the farthest point, its tidal bulges will get relaxed. So this process of tidal flexing will produce enormous energy, okay, that can lead to producing enough heat to melt Io's interior. So what we're interested in is based on Juno's gravity data to see, can we measure how much of the tidal deformation actually happens that we can relate to understanding Io's interior structure. So this slide shows two artist illustration of what Io's interior might look like. The one on the left has a global magma ocean, showing that that orange yellowish layer is melted molten rock, forming a global magma ocean between the crust and inner layer. Okay, and one on the right is mostly solid, more rigid interior of Io, and also showing that the volcanoes that you see on the surface of Io is from the local sources. So one way to measure whether Io has a global magma ocean or not is by measuring Io's tidal deformation. So if Io has a global magma ocean or liquid layer between the crust and inner layer, its crust is going to be a lot easier to deform, just like water balloon, okay? And compared to more rigid and more mostly solid interior. So in simple terms, if Io has a global magma ocean, its tidal deformation will be large, causing more changes to its gravitational variation. On the other hand, if Io does not have a global magma ocean, its tidal deformation will be small, so that its changes to gravity field will be small. And Juno acquired the data to address this question as part of the extended mission. So the Juno navigation team and the operations team went through a heroic effort to make these two flybys that occurred back in December of 2023 and February of 2024. I mean, if you think about how far the Io is from the Earth and how fast they're moving, I mean, just to give you some numbers, during the flybys, during the first one, Io was 650 million kilometers away, and second flyby, Io was about 750 million kilometers away, moving at speed of many tens of kilometers per second. I mean, tens of kilometers per second. So trying to figure out all this optimal geometry that allows us to sample tidal signature so that we can measure the variation or differences in gravity was a very challenging engineering problem, and our science and navigation and engineering team has done it seamlessly. So during these two flybys, Juno spacecraft acquired NASA, what we call the radiometric Doppler data by communicating between the Juno spacecraft and the NASA Deep Space Network on Earth, or DSN. I mean, you guys know that DSN has all these dishes with a diameter of 34 meters and 70 meters. Okay. And these measurements are so accurate, despite the fact that the spacecraft moves at speed of many tens of kilometers per second, we can actually measure the speed of spacecraft to on the order of 20 to 30 micrometer per second. So if you recall the fact that the thin human hair is about 20 to 30 micrometer per second is just astonishing, the measurement accuracy. And which also highlights that the YDSN is the national asset and allows us to explore our solar system and beyond. So anyway, over the past year and a half, the Juno science team processed the Juno gravity radiometric data combined with all historically available IO observations. And we summarized our result, which should be, I believe, it should be online by now, published in journal Nature that just came out, and the link to it should be available in the NASA press release that should be available in a few minutes. So what Juno science team has found based on the data collected during 2 IO flybys together with the historic observation is that IO's tidal deformation is not consistent with IO having a global subsurface magma ocean. So our data suggests that theory 2 is correct, and this last slide shows that an artist's illustration of what Juno science team believes IO's interior structure would look like. Okay. So with that, I'll be passing this button to Alessandro.
Thank you, Ryan. So, in the occasion of the same flyby made by Juno around Io, could not lose the opportunity to turn on the cameras on board Juno and observe Io's surface, both in the visible and the infrared. The infrared, by the way, is particularly well suited to observe the volcanic features of Io, right? So thanks to GIRAM, which is the Jovian infrared auroral mapper on board Juno, we observed specifically a lake on Io, which is Loki, and found islands on that. So what's so special about finding islands on a lake? It's because this is not a water lake, that's a lava lake. Okay, so not the kind of islands you would like to have an holiday on. In the following of the presentation, I'll show you why this is challenging our understanding of the volcanism of Io. But before that, it's important to point out that Loki is not just a lava lake, it's a lava sea. It's basically so gigantic that if you move it from Io to the Earth, scale it, that would fill basically the center of the Mediterranean Sea. So Italy is the green region on the right, basically. As you see, it's gigantic. It's 120 miles wide. If you're sitting on one side, then you won't see the other side because it's too far below the horizon, and poor you. So it's a unicum in the solar system. It's something like the greatest spot or Mons Olympus on Mars. It's something that there's no counterpart. Okay, that's it. Let's go to data. No, there's something wrong here. There's a missing slide here. No, there's a missing slide. That's the one we did. Okay.
Oh, you're right, the one with the...
Yeah, all right, no problem. I'll talk with this. Okay, so, well, we have infrared images and we have visible images. Visible images were taken by Voyager 45 years ago. Visible infrared images were taken by GIRAM on board Juno. So remember, this is a lava lake, so liquid is hotter than the terrain, all right? That means that what is colder in the infrared means land, okay, and it's darker. So by comparing visible and infrared, we were able to tell how many islands are actually active and staying there after 45 years, okay? Those islands are actually visible in the bottom part of Loki, actually not in this picture, but in the one that's supposed to be here. All right, so we found like 20 or more of those islands. They are like 3 kilometers wide. They are 10 kilometers apart. And what's so surprising about finding islands in a lava lake? Maybe the same as islands in a water lake. Not so true, because Loki, as I mentioned, it is a unicum. It's gigantic. It's producing 10 millions of watts, okay, of power continuously. As a comparison, that's the same amount, roughly, of the all humanity using for civilization, okay? So it's an enormous amount of power. So one can think about, okay, why? If it's so powerful, then the island should have been submerged, eroded, destroyed by this lake, which is not. So that's why this is challenging our understanding of Loki, because those islands are still there after 45 years. Right, so let's go to a part of the movie that Scott already presented. This is the part specifically related to Io and to Loki. So this is a Loki Patera. You're seeing those islands. In particular, we're also seeing a central island, which was already known, which is really flat. It looks like the Antarctic sea ice. It is a part in which you have channels flooded by lava. And so the idea is a flat island over a shallow lava lake or lava sea. So everything is pointing in the direction of a shallow lava lake in which no convection, and why the islands are still there is still a mystery. However, there is no current understanding of how those islands are formed. One possibility is that those islands are just remnants of the initial surface of Io before the collapsing of the caldera that formed the Loki Patera. So those remained just as pillars, okay, standing for a very long time. Or maybe, because the lava lake is so shallow, maybe those are just parts of crust, because the lake is basically frozen, so there is crust on top. So crust that is not sinking, but because the lake is so shallow, they're touching base to the seabed and getting anchored. So that's another theory. In any case, what's so interesting is that Loki is not the only lava lake on Io. We found 40 more using the same instrument, GIRAM, which were not previously understood as lava lakes. Those are smaller. They work in a slightly different way. That's the reason why you're seeing this animation here, which is a piston movement up and down. So what do we think is happening now? So Ryan told you that because of the enormous gravity stresses that Io is subject to, then it's squeezed, and maybe the magma, the melted rock, can be get out of the pores and produce movement like this. And because Io orbit is circular and it's periodic, so it should go up and down at the same period. Because the surface is crusty, okay, you don't see a lot of emission, but the surface of the lake, so the crust, gets abraded. There's abrasion on the borders because it is interacting with the borders of the lake, and this is producing the exposure of fresh lava, which is the signature that you are using with GIRAM to understand what is a lava lake and which is not. Okay, that said, you may question, okay, so what's so important about Io, understanding Io volcanic also? Well, in my point of view, it's because Io, first of all, is the gas fuel supplier for the magnetosphere of Jupiter. So Io gets a lot of energy from Jupiter via gravity and returns a lot of material, which is important as a fuel for the magnetosphere of Jupiter, which is the most important in the solar system. It gets 1 ton per second, okay? Second thing is that you cannot notice there is a white line connecting Jupiter and Io, and that's a magnetic field line. So Io and Jupiter, they are magnetically connected. You can think about this magnetic field line just as a guitar string. A guitar string has 2 endpoints. One endpoint is Jupiter, the other endpoint is Io. If you look at Io, then you have the vibration which propagates down to Jupiter. This vibration is also carrying particles and energy, producing a phenomenon when it arrives at Jupiter, which is called the Io auroral footprint. This is important because it's an extra auroral feature which is not, unfortunately, present at the end. It would have been a beautiful movie, but unfortunately it's not. And learning from this, we can know a lot because we know something occurring at one endpoint of the guitar string, what's going on to the other endpoint of the guitar string, and this way we can understand what's going on in between, which is the huge magnetosphere of Jupiter. And with that, I think I leave the microphone to Heidi.
Thank you, Alessandro. So I'm going to be sharing fresh volcanic features and a special observation of actively flowing lava on Io from Juno's visible wavelength imagery. And I'm going to kick that off by taking all of our breaths away with this stunning image of Io's North Polar region that was collected by Juno's public outreach camera, JunoCam. And I love this image because it just really shows what a primordial fantasy land Io's surface is. And the real stars of the image, of course, are the striking mountain peaks that you see so well now for the first time because of the great lighting that Juno has available from the orbit. And these mountains are actually not volcanoes, like some of the mountains on Earth are volcanoes. But Io's mountains are often closely linked to volcanoes, and I'll be talking a little bit more about that. Now, this is an incredibly dynamic surface that is constantly turning over because of all the volcanic activity. And this is a map of changes on the surface since the time of Galileo or New Horizons that were observed from JunoCam's high-resolution imagery. And we're just seeing dozens of fresh new lava flows and new volcanic deposits or modified deposits. It really shows you how dynamic this place is. This is one really striking example of that kind of change where when Galileo imaged Kanehakili, there wasn't a whole lot going on inside the blue circle, but when JunoCam imaged it this year, we are seeing these fresh, dark, long volcanic flows with diffuse gray deposits around them and a 90-kilometer-long diffuse red deposit that's coming out from the source of the volcano that's probably elemental sulfur because it's so brilliantly red. Now, changes also happen much faster on Io, and this is an example of a very rapid change. The dark dot that's in the center of both of these images is the new Patera, and just between the time of February and April of this year, this brilliant red ring formed around the Patera, and it's about 1,100 kilometers in total width, so it's a very impressive feature. And being bright red, this is also probably elemental sulfur. Now, the Stellar Reference Unit is looking at the surface of Io in a little bit of a different way. It's a low-light camera. It is a visible wavelength camera, but it's also very red sensitive, and it's actually the spacecraft Star Tracker. So what we're looking at here is the night side of Io, and it's gently illuminated by Jupiter shine, or scattered sunlight from Jupiter. And the feature that you see in the middle of the image on the right that's been projected to Io's surface is the Zalmontes Patera complex. And there are a lot of very interesting things going on in that place. So this next image is taking a zoom in of that region. So what you see with the orange arrow is a 41-kilometer fresh flow of new lava since the time of Galileo. And what's interesting about it is that the contour of it is really mirroring the contour of the mountain. So one possibility is that fresh lava found a sneak path to the surface by going up an existing mountain fracture. And the other thing that I like in this image, because it is really showing the dynamics of the surface, is the feature that's circled in white. And we haven't seen anything like this since Prometheus was imaged by Galileo in 1999. It's a diffuse, bright streak that's radiating away from one of the fresh flow lobes. And that could be a low-angle jet of sulfur dioxide frost that's being vaporized and shooting away from the lava as it crawls across the surface. So Io might have actually been hissing at Juno when we took this picture. I like imagining the sound of that. Now, because the SRU can see in the near-infrared, we were also able to see multiple areas of active lava breakouts in this region, which are circled in red and pointed to with the arrows. And some of these are really unprecedented. The first one that's shown in all of these panels is this snake, this elongated, curvy feature of emission next to the mountain in the south. And it was actually also observed in some much lower resolution GIRM imagery from May of 2023. And because it looks so similar to the two known lava channels on Io, one of them is shown in the panel on the left, our favorite explanation is that what we're seeing is the glow of the thermal emission of active lava as it's flowing along a channel. And the other first-of-a-kind observation is this little glow of lava right at the base of the mountain that you see in the right panel. That's never been seen before on Io. But if we look back at the sunlit imagery of the same mountain that was taken by Galileo in 1977, we see a vertical mountain fracture that runs from the top of that mountain all the way down to the place where we see that SRU glow. So one possibility is that that fracture extends down into the surface and created a fissure vent for the lava to reach the surface. So both this and that new flow that I showed you could be examples of volcanoes that formed as a direct result of the tectonics that formed the mountains that they're nearby. Now, the final image that we want to share is of the southern hemisphere of Io. This is another image that the SRU collected on the night side, illuminated by Jupiter shine. And the feature that's highlighted is the big flow field, compound flow field, Masubi. And it's been getting bigger and bigger since it was observed by Voyager 1 in 1979. And the SRU sees continued expansion and also 2 new flobes with multiple lobes that are pointed to with the yellow arrow. And this was an image that was collected in April, and at that time, the total length of all of the flows in Masubi was 1,600 kilometers. So it's actually the largest currently active flow field in the solar system. So just goes to show you, Io is a pretty unusual and very interesting place. And with that, I'll hand it back to Liza.
All right, thank you, panelists. We will now open the floor to questions here in Washington and online. Do we have a taker? Raise your hand, and we'll bring you a mic. We have a question online.
Yeah, we have a couple of questions online. Our first one is from Leo Enright on Irish TV for Alessandro. The piston movement in your animation, do you care to hazard a guess as to how much movement there is? Meters or kilometers?
Yeah, thank you. This is a crucial question. So the movement should be at least a few meters or tens of meters, otherwise the crust would not break. So we think it's probably proportional to that. We still don't have models for predicting how wide should the movement, but we think it would be of the other tens of meters. That would be realistic. Also because that would be of the same size of the part of the crust which is eroded. So our rough estimation would be that.
And a second question online.
Yeah, we have a question from Richard Lovett, who's a freelancer. How do you know the lake is shallow? And was it speculated at one point that the islands are floating?
Okay, so the island cannot be floating. Thank you again. So the island cannot be floating because they are in the same position for 45 years and there are 20 more. So for sure they are anchored. So anchored lava islands, they challenge the possibility of having a very deep convective lake, because convective lake would have been eroded those islands. So that is really hard to predict, to reconcile with the models we have for Loki. So basically also the fact that they are very packed. Okay, so you may think about those kind of Pacific islands in which they are like very close each other and in a shallow part of the ocean. That's an analogy.
Anyone in the room like to ask a question?
She has another one.
Oh, go ahead then.
Yeah, we have another question from Leo. This one's for Heidi. The huge sulfur ring that suddenly appeared, what is the emplacement mechanism? Is it coming up from below or is it a deposition?
Those kinds of rings are usually pyroclastic, very, very explosive events that are coming up from below. Those red rings, sort of like Pele, if you know that iconic ring, yeah.
And we have a follow-up from Richard. Can you speculate on how deep the lake is? He wants to know how shallow is shallow.
Okay. So we have a model in the paper which is submitted, in which we speculate that at least it should be a few tens of meters. Otherwise, the latent heat from the magma crystallization won't be enough to produce the rate at which the crust is cooling down. So it's difficult to constrain, but I would say that at least 10 or 20 meters would be necessary for sure. The other boundary is really difficult to tell because we don't have models for this. We can maybe infer that in the future paper by using like speculation on how much power is stored in the lake and regularly flowing out, but it's difficult. Also because we don't have models for the formation of islands. So formation of island first and then the depth of Loki.
Hi, Kasha Patel, Washington Post. So for this theory too, I mean, that sounds very similar to how volcanoes are operating on Earth. Can you draw some more similarities about what we're seeing there and how that is here on Earth? And are there any places, like any analogs here on Earth that you or your colleagues are looking at that we can compare this to and learn more?
So, yeah, I can probably address that. So the rocks are partly molten at Io, which would be somewhat similar to what we see in Hawaii and maybe in Iceland. So there are a lot of similarity between how the volcanoes may work at Io versus on Earth. But that's the detailed analysis that will be, I mean, within the science team in Io, in Juno science team, we've been talking a lot about the similarities between how volcanoes work on Io and on Earth. And we found that there's a good similarities between Hawaii and Iceland. And furthermore, detailed studies is currently going on. And that's probably something that we'll be doing once this paper comes out, so that there will be more opportunities to look into this.
Yeah, I'll just add something for you there. So one of the basic question was whether there was a global magma ocean underneath driving all of these things. So the Earth doesn't work that way. It's more like individual capillaries coming up, right, that are creating it. And so the results that Ryan presented show that the volcanic activity, at least in that regard, is more similar to the way we see it on Earth than this other option where maybe the squeeze was so much that you had a whole ocean of lava underneath that was, feeding the global distribution of volcanoes. So that you can add that in as another, possible Earth analogy.
Just kind of a follow-up, what does this theory tell you about perhaps the evolution of how, like, the moon was there? I mean, I guess compared to, since we know how it kind of works on Earth, I mean, what can you extrapolate from Earth to understand more about Io or vice versa?
Want to take that one, or I mean, so it's not, I think we still have to study and understand the real similarities and differences. That's the key, actually, to science, not just NASA planetary science, but all science works with comparative study in order to try to understand something. You look at an apple and you look at an orange and you try to see what's different, what's the same, and then you understand fruit, maybe. So looking at across the solar system at different moons and planets and other things and comparing them, you definitely learn. And that is basically, what a further investigation will be, is to try to understand the mechanisms that we can study here on Earth much closer, and then try to understand what's similar and different with Io. So I think that hasn't really been done yet. But there are basic questions that had to do with the global magma ocean that were more universal in the cosmos and astrophysics, and that tidal forcing is a very common idea that we think is going on, and that it's a way of generating heat when you're not really close to the sun, right? So the whole idea of ocean worlds and moving the habitability zone away from Earth and possibly having habitable zones at the giant planets and maybe other places throughout the cosmos, tidal forcing opens up an ability to get that energy that you would need. And one of the basic questions was, okay, so early in the solar system, when you had tidal forcings, were global magma oceans a common thing that were being created? And so this one example that Io was our first shot at really saying, okay, this kind of thing might be being made. We don't see that it's necessary. So it doesn't mean that it doesn't happen occasionally, but it's not a foregone conclusion if you get something too close that you're going to end up with a global magma ocean. And so that is going to have to trickle into theoretical studies now of how early evolution works when you're forming solar systems and other places. Anything you want to add to that?
Yeah, maybe I can add a quick thing here. So understanding the tidal heating is probably one of the most important topic for understanding the planetary formation and evolution. For example, tidal forcing works on bodies like not only Io, but Europa, Enceladus, and many other the satellites in the outer systems. So from my personal perspective, understanding whether Io has global magma ocean or not is really a first step in really trying to understand how does the tidal forcing work and how all these how much data melting exists inside of Io, and then how does it get erupted to the as a volcanic eruptions. Those are all first steps in understanding planetary evolution. So there will be a lot of studies, follow-up studies that can be related to like Europa Clipper mission, the JUICE mission that are currently en route to Jupiter.
Hi there, Kimberly Cartier from EOS Magazine. My question is, what types of observations would you need in order to better understand the processes going on that you just described, the tidal heating and the processes generating these lakes? And I guess sort of speaking to what Ryan just mentioned right at the end, what can we expect any of those observations coming from Juno or several years from now from Clipper or from JUICE?
Well, to first order, you'd like to get really close to Io and maybe even orbit it and do things like that with a lot of different instruments. Unfortunately, we're not going to go back getting close to Io. We flew by and our orbit slowly migrates. It's a good thing because that's what enabled us to go by Io, but it continues to go inward. And so now we're moving in toward another set of moons that are co-located with the rings and these very high intense radiation belts. So we're not necessarily going to go back to Io. We will be able to study Io still from a distance and keep monitoring the volcanoes, and the infrared and the visible images are the way to really do that. And we'll certainly look at the aurora, that kind of thing, but it'll be from afar. And even with JUICE and Clipper, they don't go really close. Now, they have some things that we don't have, such as great telescopic cameras. We have a camera that was designed for Juno to really go in and over the poles and look at the atmosphere and play a role with outreach and education. They have cameras that have telescopic lenses, so they may be able to do more, and they have other instruments that they'll be able to probably investigate. But I think if you're going to, and we will continue to probably learn from this data, and models, but maybe someday we'll have a mission that actually goes back and gets close to Io that might have additional measurements.
We'll take a question from online and then next.
We just have one last quick follow-up from Richard again. He would like to know, is the other boundary hundreds of meters or kilometers? What's the scale here?
Boundary. I don't know what boundary is he referring to.
You mean the lava lake?
I believe he's asking about the lava lake. We did not get a clarification.
Okay. So again, it's difficult to tell. So one idea is that we observe the size of islands, okay? So from the size of islands, at least you can infer, for example, you can imagine that either they are pillars, can be the case, but we need more investigation to understand the nature of them, because it depends on the formation. So as soon as we will have a good theory for the formation of those islands, then maybe we can be able to tell which is the shape, how they are shaped, if they are nearly vertical or not. For example, we know the size of and the distribution of size of those islands. Those are like 3 kilometers wide, maybe less. So you cannot imagine like having a 3 kilometers wide island on top of, say, 10 kilometers ocean, which is not really, straightforward, right? So the first thing is to understand the way the islands are formed. From then, we can maybe get a better clue on how the magma ocean is deep. Also, consider that we are already ruling out the possibility of convection. So convection is not possible in very shallow lava lakes. And so that's the reason why we have a limit, an upper limit on the thickness. Still, giving a precise number at this stage is really difficult.
Hi, it's Natasha Stephen. I'm at the Geological Society in London. Given that we're not going back to Io, which is devastating, and we can't even get MSR sorted, so I assume we're not getting Io anytime soon. I guess my question is about, particularly with Loki, the lava lake or ocean, the sea, what are we expecting those rocks to look like, right? Because you say that the volcanoes are similar to Iceland and Hawaii, but they're fundamentally different volcanic systems on Earth. And if we don't have convection, we're talking about shallow lava that's been molten for a long time, those are not going to be fine-grained lavas. They're not crystallizing quickly. They're going to be really slow. They're going to be growing really large. Are we looking more at something like rift volcanism from like Erebus and Kilimanjaro in Kenya, where you get those really, really huge xenocrests in something glassy?
All right. So yeah, that's really interesting. So in the study, not only we found islands, but we also had the possibility to follow the cooling down of the crust. And the cooling down of the crust is giving us a lot of information about the crust thickness over time. Now there are theories and actually studies about the fact that Loki is subject to periodic overtone, bridenings of the lake, just as if the lava lake lost all this crust all of a sudden and then it gets cooled again. And that's exactly what you're seeing. So the idea is that one possibility that is still maybe compatible with the presence of island, but we need to study that more, is the fact if this crust is periodically sinking, okay, then what you're seeing is the fresh magma underneath the crust, which is sinking. Only part of this crust may not sink and form the island. That's the global idea. Yeah, so that's the way. In the original paper, okay, which was already published, one analogy was, as Ryan said, with the Hawaiian lakes, lava lakes. In this case, we have rims surrounding the lake because of abrasion, etc. But remember that, first of all, that Loki is an unicum with respect to all the other lava lakes. So we have a complex scenario here. We need to understand all the other lava lakes. Then we understand why Loki is so different, to understand why the islands are formed. And from that, we can maybe infer the possibility to measure the depth. It's a very hard job.
But we're not going back, so.
No, maybe not.
Anyone else in the room? We have one more online? No? We're at time. All right. Thank you to our panelists. It's been a great presentation. We're going to close the Q&A at this point, but if you would like to talk to them, I'm sure they'll be here available to talk one-on-one with you. Moving back to Earth system at 10 o'clock in the roundtable room, experts will be available to talk to you about the U.S. Greenhouse Gas Center. And we're back here at 11 for an update from Perseverance. So I hope you'll join us then. Thank you all for coming.